All right, let's see if we can talk about uniform circular motion. Uniform circular motion, which is what you have when you have an object moving in a circle uniformly. So let's draw our circle here first. Oh, that's a nice looking circle. There we go. Yeah. And then right here, of course, we will draw our object. The object has a position vector, which we'll draw in this nice blue color. So we'll call the position vector r vector. And then it's got some velocity. What's the velocity? Well, we remember from studying vectors that anytime an object is moving on a curved path, its velocity vector is going to be tangent to the path at whatever point the object is at. So, since it's right here, we know the velocity vector, well, we know it has to be going up or down. We're going to say it's going counterclockwise. So this is our velocity vector there. So what do we know about these two vectors? Well, for one thing, we know that the magnitude of the r vector, so this, which is also sometimes just a scalar r, is constant. Because that's how we define a circle. The circle is the locus. That's the mathematician fancy word. The locus of all points that are equidistant from the center of the circle. So any point that's r distant from the circle, or sorry, r distant from the center here, is on the circle. So this object travels through all those points. And then what do we know about the velocity? Well, we know that the speed, which is the magnitude of the velocity, right? Speed, we use scalar v for speed, but it's the magnitude of the velocity vector, is also constant. That's because we're saying it's a uniform circular motion. Okay, so that gives us something to play with. What's an interesting fact we can figure out here? Well, how long does it take the object to move in a circle? Let's call that the period of revolution. I'm writing it down here for a reason. You'll see it in a moment. Period of revolution. That is capital T. And we use capital T for that. So we're trying to find how long it takes this object to go once around the entire circle like that. Well, if you've got an object, you know what distance it travels and the speed it's traveling, especially if it's traveling at a constant speed, then the time it takes to travel that distance, we just take distance traveled divided by the speed. No problem. So what's our distance around the circle? Well, we should remember from a circle that the circumference of a circle, which is the distance all the way around, is 2 pi times the radius. So that's just 2 pi r. 2 pi r. And then the speed is, of course, just v. So the period of revolution right there is 2 pi r over v. Pretty easy, huh? So the question now is, where do we go? Suppose we want to figure out the acceleration of this object, and I'm going to use, let's use a nice, pretty, well, it's sort of a peach color. I was going for orange, but we'll use this sort of peach type color. Let's see. Oh, yeah. So what's our acceleration vector for this? Well, there are a couple things we can say about this. One is that we know the object is to be a constant speed. So from the fact that this is constant, we know that a dot v, the dot product of the acceleration and velocity vectors, must be 0. Remember, that's our condition for when something is not speeding up or slowing down. So a dot v must equal 0, which means the acceleration and the velocity vector must be perpendicular. I'll tell you what, I'm not going to write that, but, well, yeah, what the hell, I'll write it that way. Perpendicular. So we know then if the acceleration vector has to be either perpendicular to the velocity vector, it has to be either pointing straight out or straight in. One of the things we learned from in our study of vectors was that when you have an object traveling along a curved path, the acceleration vector will always point into the curve. So remember, it's like a motorcyclist leaning into the curve, so we know the acceleration vector points that way. So that solved that pretty easy, but then how big is it actually? So we know the direction, right? What we want to find is the magnitude, which we denote with a the scalar a, but it's just the magnitude of our vector a. What is that? Well, there are a couple different ways to figure that out. So I'm going to set one of them up. Suppose, let's go back and look at the velocity vector. Now let's recall that vectors have this dirty little secret. We draw them as arrows, but vectors have this dirty little secret that it actually doesn't matter where you put them, it's still the same vector. So I can take, for example, at this point in time, I can take the velocity vector of this black object here, and I can draw it over here, because I just feel like drawing it there. That's all it takes. As long as I draw it the same length, pointing in the same direction, it's still the same vector. So there's my vector v for velocity. Now, if I want to draw the vector velocity v later, well, I can say at this point, well, I know it's going to be pointing this way, right? So say when the object is here, the vector is pointing this way. The velocity vector is pointing this way. It's going to have the same length because its magnitude remains constant, because this is moving at a constant speed. Remember, it's just going to change. So when the object is right here, the velocity is going to be pointing out this way, but it's going to be pointing at the same distance. And in fact, as this object moves all the way around the circle, the direction of the velocity vector is going to change. It's going to sweep around, but it's always going to be the same length. Now, we just got through talking about this, but what do you call an object? What do you call it when you have all of the points that are equidistant from the center of something? You call that a circle. So this circle here, it looks about right. No, that's not right. This circle here, let's try that. Let's try one more time. I'll do it over here. There we go. This circle here, that's a pretty good one. Perfect. All right, this circle here is the circle that the velocity vector moves through if its tail is always pinned down here. So here we're drawing the velocity vector with its tail on the object that's moving, just so we can, sort of be convenient that way. Whoops, don't want that. But here we're just pinning it down to something here, and we're drawing it pointing in different directions as it goes around. So, and it sweeps out this circle. So this is going to become important. We can think of this as though sort of this over here is what we call position space, and this over here on the right side is what we call velocity space. And there are several different ways to find the acceleration. They all involve using position space and velocity space. So I'm going to go into them in the next couple of videos. I'll do one short video for each of these methods, but they'll be in separate videos to keep it concise. But every one of them is going to involve position space and velocity space, these two circles. So make sure you understand what's going on here, and I'll see you in the next video or two.